Hello students. So now let's start the processor architecture, and based on Harvard and VonNeumann architecture. These are two very important architectures, and you should know about them. And there is a memory architecture. We have classified, in my last lecture I have classified my memory architecture in two types. One is Harvard architecture and another is VonNeumann architecture. Now let's see what's happened actually in the Harvard architecture and VonNeumann architecture. First, let's see about the Harvard architecture. Harvard architecture has the CPU and another is input output devices. Now there is a memory. I have told you in my last lecture that in the Harvard architecture there is a separate memory and data program memory and data memory, both are different in the Harvard architecture. So basically let's understand by means of an example. If there is a add, there is a instruction. I am giving an instruction add a comma b. So a and b are two operands and fetch and having the content of the data. So I can say that these two contents has the data. These two contents has data. Right, and this is an instruction. I'm writing in short because I'm writing by mouse. So it is a instruction. Okay, so when we say that if it is a Harvard architecture or VonNeumann architecture, so how this instruction will store in a memory. So it is important when how a CPU basically works, because CPU works on a clock cycle basically. So there is a clock cycle, that is a clock cycle on which the CPU works, and on the base of the clock cycle it defines that how this is working actually. So add this instruction, this one of the instruction will be stored in case of Harvard, it will be stored in program memory, and the data will be stored in the data memory. Both will be stored in a different memory structure. While in VonNeumann, both the things will be stored in a fashion like that. If it is a memory, so first your program memory for first of your instruction will be stored, means add will be stored here, right? Then data will be stored in the next consecutive location of the memory, means if it is a 0, it is 1, it is 2. While in that case, if it is a data memory and code memory, so add will be, it is a code memory, so I am writing CM for code memory and DM for data memory. So my data will be stored in that case is this. So that is a CPU. That is a CPU. So basically it fetch both the things in a single cycle, in a single amount of cycle. In that cycle it will be able to fetch both the data as well as the instruction, right? In this next cycle it will operate on it, and in the next cycle it is fetching of the data, it is operating on the data in the next cycle, and in the next cycle it is storing the result, right? That happens in a Harvard architecture, and it is good. While in that case, add will be fetched first, this instruction will be fetched first, then the operands will be fetched, means fetching is in 2 cycles basically. Then that of this operation, if I compare with this operation, and this operation, then fetch cycle will contain around 3 cycles. 3 cycles are for fetching, while in that case only 1 cycle is needed for fetching, right? So the speed of Harvard architecture is more than that of the von Neumann architecture. Okay, so likewise this it works basically. It will first fetch the add, then A, then B, then operate on it, then operation cycle will be there, and then it will store the result in A location, right? So the number of cycles in a von Neumann architecture are more than that of the Harvard architecture. So that is a main difference between two things, and it is very much used in different type of the architectures. So von Neumann were the scientists who developed this, who provided this architecture in the market, and Harvard is the university, and in Harvard University this type of architecture was made and developed, and it was very much used in microcontrollers. So that is mainly used in the microprocessors. So this type of architectures are used. So thank you for this lecture. In my next lecture I will tell you next things. Thank you.